Okay. So in the last class, we had studied, or we had basically started with link state algorithms. And as an example, we had done Dijkstras algorithm. Okay, so this was the last example that we had done. And we found out that how do we, with the help of Dijkstra's algorithm, when the states of all the other nodes are available to us, it is kind of a centralized algorithm, the link state algorithm, because we are basically having the information of all the nodes present in the graph, right? So with the help of Dijkstra's algorithm, we can get the shortest path or shortest cost path from a given node to all the other nodes present in the graph. Okay. So today we have to start with the a short discussion on Dijkstra's algorithm. Okay. So first, whenever we are doing any algorithm, you have already studied in your data structure and algorithm class that whenever you are looking at the algorithm's features, you basically look at that what are the characteristics the algorithm presents in terms of complexity, right? So here also we are basically looking at that what is the complexity that Dijkstra's algorithm will provide. So here, as you can see that. If you remember previous class when we were looking at Dijkstra's algorithm, so we had around n iterations, and in each n iteration we need to check all the nodes which are not in our set n dash. Actually, it should be n dash here, not n. So the number of comparisons comes up to be as n times of n plus 1 by 2, leading to a complexity of O of n square. Okay, but you have already studied data structure and algorithms course where you know that how to implement Dijkstra's algorithm with O of n log n complexity. Okay, so this I will not go further as to how do we get this complexity because that has already been covered in your previous courses. But what we have to find out is that how do we achieve this this state where we can actually use Dijkstra's algorithm. Okay, and there comes the issue of message complexity. That means how we are communicating with other nodes in terms with respect to messages, so that all the other nodes present in the network actually get the information of each other, right? So first point, as we can see here in message complexity, that each router must broadcast its link state information to other n routers. Obviously, because we need to know the information of all other nodes present in the network in order for this algorithm to work. Now, if we want to broadcast our a particular node's information to all other nodes present in the present in the network, in that case, we need to have some efficient broadcasting algorithms. Okay, so we should have efficient and interesting broadcasting algorithms such that O of n links, O of n link crossings are required to disseminate a broadcast message from a source, from a given source. Now, each router's message will cross O of n links, which will lead to an overall message complexity of O of n square. Okay. So, as n will increase, your message complexity will obviously keep increasing. Okay. So, which is the reason why Dijkstra's algorithm, even though it seems to be very easy and if the information is known, you can also cover it in O of n log n time with the O of n log n complexity. But the problem is that you need to know the link state information of all other nodes, and which again increases the message complexity when n is large. So another issue that happens in case of Dijkstra's algorithm is that route oscillations are possible. Okay, that means the change in routes that a particular node, if you want to reach from a particular node to another node, then within a given time, change in routes may happen. Okay, and that is known as route oscillation. As an example, it is given here that if you want to go to destination A, okay, and the traffics are entering from D, C, and E with rates 1, and E is less than equals to 1. Okay. So in that case, the link costs, which are directional and they are volume dependent. Basically, the cost that is there between two nodes, that is on the edge that has been mentioned, these costs are directional, that is from where to where the traffic is going, and it is volume dependent. Okay. Now, initially, as you can see in the diagram here, initially there is traffic entering from B, C, and B. It should be B, not E. Okay, D, C, and B. And the traffic entering is at rate 1, E, and 1, where E is less than 1, as has been given here. Now, given this cost, okay, when the arrival rate of traffic is changing, then the cost will also change on the edge, right? So given these costs, you have to find the new routes, okay, which will result into, so you have to first calculate the new cost that is coming, and accordingly you will calculate the new route. Okay, so with this, now you can find out that the route can change. All right. So here also, that again, if the cost changes, then you have a new routing, and then it will create a different path altogether. These kind of route oscillations are generally possible in case of Dijkstras algorithm, okay, because the link costs are directional and they are dependent on the traffic volume. Okay. So now, today basically, actually, we are going to start with second kind of algorithm, or second category of routing algorithms that we were looking for, and this category is our distance vector algorithm. Okay. So in the link state algorithm, we had the information of all the nodes present in the network or the graph. But in case of distance vector algorithm, you do not have the information of all of the nodes in the network. Okay. Basically, you get to know the information of other nodes in the network with the help of information that a node gets from its nearest neighbors or directly connected neighbors. Okay. So we'll start with an example of distance vector algorithm, and that is based on Bellman-Ford equation. Okay, that uses dynamic programming. So Bellman-Ford also you are aware of. So the main the cost function that we are basically looking for, that is, if you want to get the cost from node X to node Y, which is denoted as dxy, then this is calculated as minimum of V cxv plus dvy, and V being an intermediate node between X and Y. Okay, so you are trying to find out that what is the minimum cost, or what is the least cost path from a node X to Y with the help of this equation, Bellman-Ford equation. Okay. So what is CXV? CXV is the direct cost of link from node X to node V. dvy is the V's estimated least cost path to node Y from node V. Okay. This minimum is taken over all neighbors V of X, and of course dxy is nothing but the um, the least cost path from X to Y, cost that you incur. Now, this is an example for Bellman-Ford algorithm. So here too, as in the previous example that we had done in the last class, that U is the source node, okay, and Z given here is the destination node. So we have intermediate nodes as X, Y, B, and W. So as per Bellman-Ford algorithm, the equation that we have just seen in the last slide, if you want to find out the distance from V to Z, that is dVz, um, here it is coming out as 5. Okay, so let's see how it's coming out as 5. If we want to go from V to Z, what are the different paths? You can go via W, or you can go via X and W, or you can go via X, Y, and Z. Okay, so if you go directly via W, then it is going to cost you 8, right? Whereas if you go from X, then W, then Z, then also it will cost you 10. And if you go from V to X to Y to Z, then it costs you 5. Okay, so it seems that the minimum is 5 here, and therefore the dvz value is given as 5. Similarly, for dxz, the minimum value is 3, and for dwz, this is the minimum cost path between W to Z, and it is given as 3. Okay, so if you traverse from W to Z via Y, then it is costing you much lesser than the direct link that you have between W and Z. Okay, now how do we calculate the Bellman-Ford equation? Okay, or how do we make use of the Bellman-Ford equation? So if you want to have a destination, a source U and a destination Z. Okay, so in that case, how to find the least cost path? That will be given by minimum of CUV plus DVZ. That is, if you want to go via V, then what is the path? What is the cost of that path? You go via X, what is the cost of that path? And what if you go via W, then what is the cost of that path? And then find out the minimum value. Okay, so see, U is connected to V, X, and W directly. So now when we are trying to find out the distance from U to Z, so you first find out what is the cost that is incurred if you move from U to V, or U to X, or U to W, and then you try to find out that what is the cost of the rest of the portion to your destination. Right? So here, as you can see that if you try to find out that what is CUV plus DVZ, you will find out that CUV is basically 2, and DVZ is nothing but 5. We have already seen that here. So that gives you 2 plus 5, CUX plus DXZ gives you 1 plus 3, and CUW plus DWZ gives you 8. So the minimum is 4. That means the minimum cost path from U to Z is via X. Alright. So the node that achieves minimum of X is the next hop on estimated least cost path to destination Z. Okay. Now, the key idea, what should be the key idea for distance vector algorithm? In link state, we need to know the information of all other nodes while using that algorithm. Okay. Whereas in case of distance vector algorithm, the key idea is that the information of the neighboring of all the directly connected nodes has to be sent by a node in a regular or a periodic manner. How will this help? This will help the distance vector algorithm to have a better estimate of the status of the neighbors. Okay. So when a node X receives a new distance vector estimate from any neighbor, then it updates its own distance vector. Okay. And this updation is done using the Bellman-Ford equation. Okay, so please understand the scenario that's happening here, that you do have a graph with a set of nodes and edges. Edges are basically representing the weights, okay, that is there between two nodes. Now, the key idea behind the distance vector algorithm that uses Bellman-Ford equation is that you have to update the distance vector estimate of each neighboring node in a regular or a periodic manner. So, how is it done? That all the nodes which are in direct communication to a given node, they try to get the estimate of the next hop neighbors and then send this distance vector estimate to the current node that we are considering. Okay, so once this node gets the information of all other nodes in this manner, or once this node gets any distance vector estimate, so then it tries to update its own distance vector using this Bellman code equation, and then whenever it has to take a decision as to what should be the minimum cost path from from a given node to a given destination node, then in that case this information will become handy for that. Okay, so how do we get this information? So dxy, as we know, that is the minimum cost path from x to y, is given by minimum of v cxv plus dvy for each node y belongs to n. So there's just one note here which we need to note, that under very minor and natural conditions, the estimate of dxy converges to the actual least cost small dxy. So how is it different? How this algorithm is different, and how does it work? So first, what happens at each node? Okay, so first thing that each node has to do is that it has to wait for a given change. Otherwise, there's no need to update its table, right? So it has to wait for a change to occur, or basically change in its local link cost, or it waits for an update or a given message from its neighbor so that it can update its table. Okay. Once that is done, what it does is that it recomputes the distance vector estimates using distance vector received from the neighbor. Now, if there's any particular destination or any particular node in the network that has changed or whose link has changed, then it is its responsibility to notify the neighbors about it so that they can also update their distance vector estimates or distance vector table. Okay, so this is an iterative process. Now, the distance vector algorithm also is an iterative and asynchronous process where each local iteration is basically caused by some either some local link cost change or a distance vector update message from a neighbor. Okay, if the link is broken or if the link is not working, then the update message that is received from the neighbor that will have to be updated at the source side or at the given node's side. Now, another feature of the distance vector algorithm is that it is distributed in nature and it is only self-stopping. Okay, so we know that what is a distributed nature, that is each node will notify its neighbors only when its distance vector changes. Okay. Now, these neighbors, they will notify their neighbors only if it is necessary. And if there is no action taken, then in that case, no notifications are received. So this is an example of a distance vector algorithm. So how does it work? All the nodes in the network have a distance, estimates to the nearest neighbors only. So you can see that the node A here has distance estimates of its nearest neighbors. So A to A, of course, it's going to be 0. It is directly connected to B and D. Okay, so if you see the corresponding costs here, DAB is a direct connection between A to B, therefore the edge weight is given as 8 here. And then the other one is DA to D, and that there the edge weight is given as 1. Okay, for rest all others, the edge weight is given as infinite because there's no direct link from A to the corresponding nodes. Now, there are a few asymmetries also in this scenario where it is mentioned that if there is a missing link at this juncture, that is C and F, then it might have a larger cost. Why would it have a larger cost? That we will see eventually in this chapter. But the uh, if the condition of a particular link keeps changing, then the updates also have to be done regularly, thereby increasing the complexity. Okay. Now here an example is given where t equals to 0, where at t equals to 0, all the nodes have distance estimates to nearest neighbors only. Okay. And what is done at time t equals to 0? All the nodes, they send their local distance vectors to their neighbors. Yeah. So this is how all the nodes they send their local distance vector to their neighbors. Now at t equals to 1, let us check what happens. Okay. So what would happen that each of these nodes are going to receive the distance vector estimates of uh, their neighboring nodes or from their neighboring nodes. Okay. Now once they receive these distance vector estimates, then they compute their local distance vector. Okay. So they get the information of all other neighbors in the form of distance vector estimate, and then they try to update their own distance vector estimate. Now once this is updated, then they send their own distance vector estimate to their neighbors. Now this happened at t equals to 1, and then t equals to 2. What happens is that all the neighbors, I mean all the nodes, for all the nodes, what happens is they receive distance vectors or distance vector estimates from their neighbors. Then they compute their new local distance vector and then send their local distance vector to their neighbors, and so on and so forth. So this entire thing kept on happening twice. I just showed twice. So that is an iterative computation. It will keep happening, so on and so forth in the network. Okay. Now let's take a look at the iterative computations at nodes. Okay, so this is the same graph that we are having. So at t equals to 1, what happens? B receives the distance vectors of nodes that are directly connected to it. That is node A, C, and E. Okay. And what is the current distance vector in B? So the B to A is 8, B to C is 1, B to E is again 1, and there's no other direct connection. So therefore, for all other nodes in the network, the value or the distance vector estimate is infinite. Okay, so this is the content of B's distance vector at this point, and at t equals to 1, B receives the distance vectors from A, E, and C. So what is A's distance vector? A has direct connections to D and B. So only for D and B we will have the corresponding values of 1 and 8 as distance vector. A to A is of course going to be 0. And for all others, the distance vector estimate is going to be infinite. Similarly for C, so only from C to B we have a direct connection. For all others we do not. So only for C to B we have 1, and C to C is of course 0, and rest are infinite. Same will be for E also. For E also, we have like 4 different connections to B, D, F, and H. Okay. So DB is 1, DD is 1, DF is 1, and DH is 1, and DEE is equal to 0 because it's the same node. So these are the distance vectors for different nodes present in the network, and they are now getting exchanged. Okay, so t equals to 1, B receives all these updated or all these distance vectors from its neighboring nodes. Now once it receives that information, it will compute and then basically update its own distance vector table in order to get the most updated information. Now, how to compute this? This computation is done using Bellman-Ford equation, as we have already studied earlier. So for dBA, okay, so it has received the distance vector from A, it has received the distance vector from E, and it has received the distance vector from C. Okay, so using Bellman-Ford equation, first it is being written here is that dBA is equal to minimum of CBA plus DAA. Okay, so CBA is 8, but DAA is 0, right? Then CBC plus DCA, that is cost from going from B to C, and the distance vector from C to A. Okay, so distance vector from C to A here is infinite. That is what we have received. All right, and the cost from B to C, of course, is 1. Then again from CBE. Okay, so cost. So if you have to find out the cost for the destination A from B, okay, so you have to find out that CBE, that is what is the cost from B to E, and the cost from corresponding E to A. Okay, so we know that that is also infinite, so then it becomes infinite, and the minimum is 8, so that cost becomes 8. Similarly, we can compute dBc, which is equal to 1, dBd equals to 2, and dBe equals to 1, and so on and so forth. So we are finding out the costs from a given node to all the other nodes present in the network. Okay, so dBA, dBc, dBd, dBe, and dBf. So we have found out all of these information, and also dBg and dBh, then dBj, and so on and so forth. So this happens at time t equals to 1, and accordingly the distance vector in B is updated. So as you can see earlier, we had in distance vector of B as dBA equals to 8, dBc equals to 1, dBd equals to infinite, whereas here you get dBd equals to 2. Okay, see here dBd, you can see here that if you calculate dBd, you get it as 2. Right? So this is the computation that's happening at B, and with that the distance vector in B has been updated with dBd value equals to 2. Okay, dBe value is equal to 1. dBf was earlier infinite, now it is 2. Okay, so if you can see here for dBf, it has been found out with respect to these set of um, values. So minimum of CBA plus DAF, CBC plus DCF, and CBE plus DEF. So these two, that is the CBA plus DAF and CBC plus DCF, these are the values are infinite, and for the last one it is 2, and hence therefore this is the corresponding dBf value that we get, and it has been updated in the B's distance vector table. Okay. So this is how we calculate the distance vector estimates for each of the nodes present in the graph. Alright, so this has been now overwritten on top of what was already there at B. Now let's see what happens. So at time t equals to 1, C receives the distance vectors from B. So then C will have to compute its new distance vector updates. Right, so what does it do? So using Bellman-Ford equation, we calculate that what should be the updated value of the distance vector estimate at C. So we found out DCA, DCB, DDD, and so on and so forth, corresponding to what are all the other nodes in this particular network. Okay, so this is how this is being calculated here, and we find out the corresponding distance vector values for A, B, C, D, etc. Though there we have some non-infinite numbers, whereas for all others we do not have any direct link, and hence the values are given as infinite. Okay. Now this is being overwritten with the newly updated one. Similarly, for all of the nodes in the network also, this will continue, so on and so forth. Okay. Now, this is an example again that once all of this information is received at the node in the middle, that is E, then how does it compute? So we can see that we can actually compute using our Bellman-Ford equation. So I will not go further into this part. Uh, let's see. So just a summary, iterative computation, distance vector is nothing but state information diffusion using iterative communication and different communication steps or computation steps which diffuse the information of a given node through the network. Okay, so basically, as you can see, that periodically every node is sending its distance vector estimate to its neighbors, which are directly connected to it. Okay, so with the help of this, what happens? A given node gets to know that how will it get the or how much cost will it cost this particular node to if there is a packet that needs to move from the node to any other node given in the network. So this is how the estimate is done, and this is how the estimate actually helps all the nodes to get maximum information of its neighbors. So here's an example that has been given. So suppose at t equals to 0, C state at t equals to 0 is at C only. That means C only knows its own state at t equals to 0. At t equals to 1, what happens? That this distance vector information of C has now propagated to B. Okay. Now, this information that B has actually received, this information may influence distance vector computations, and that too up to one hop away. Now, at t equals to 2, what happens? Okay, so C state at t equals to 0 may now influence distance vector computations up to 2 hops away. Okay. So with this estimate that we are getting from C to B, now B is updating its own distance vector algorithm, distance vector table, and then that again is when it is shared that information of the route between any other node to B, when this information is being calculated. So in that case, this distance vector algorithm is able to compute the distance vector up to 2 hops away. Okay. All right. So this is equal. What happens at t equals to 3 and t equals to 4. So let's not go through this right now. Let's jump to the most important one. That is the a new concept that we are going to study about distance vector algorithms. Okay. So this is a very important concept. So please pay attention to this part. So, what have we known of distance vector algorithms? That if there is a change in the link, then in that case, that information has to be sent over to the neighboring nodes. Okay. So here, let us take an example that we have three nodes here, X, Y, and Z. The edge weight originally between x to y is 4, between y to z is 1, and between z to x is 50. Okay. Now, if there is a change in the link cost, in one of the links, the cost has now changed. So it is the responsibility of the corresponding nodes which are connected to that particular link to detect this change and do a local link cost exchange. Okay, if it is required. Now, once this is done, then the routing information is updated, and then again the distance vector is recalculated. Okay. Now, if the distance vector changes, then only the neighbor nodes are notified about it. Okay, so this is the concept here, that is good news travels fast. So suppose at time t equals to 0, the node y, it detects that there is a change in the link cost. Okay, and then updates its own distance vector table, and then it does its job of informing its neighbors about such a change that has happened. So now, what would happen to Z by now? Okay, so at time t equals to 1, the node Z, it receives the update from Y. Okay, so once it receives the update from Y, it will again update its table. It will compute new least cost to X, and then it will send its neighbors to its D. So at t equals to 1, as of now, we have seen that Z receives the update from Y. It updates its own table and computes the least cost path to X. Okay, and once it does that, it sends that information to its distance vector, or it sends the distance vector information to its neighbors. So similarly, at time t equals to 2, what happens is that Y receives Z's updates. The updates are nothing but they are on distance table, and Y's least cost, they do not change. So Y does not send a message to Z. Okay. Please pay attention at this part. At time t equals to 2, Y receives Z's update. So here, Y will receive Z's update at time t equals to 2. It will update its own distance table. But what happens in this case is that Y's least cost, they are not changing with this update. So Y does not send a message to Z back. Alright. So now, where will this problem occur? See, earlier in the previous slide, what was happening? That the cost was reducing. We had a cost of 4 between x to y, and there was a reduction in the cost. So then what happened, as you can see at time t equals to 2, y's least cost did not change, and therefore y did not send a message back to z, but z actually um, uh, received an update once this change was done between x to y, when once the cost was changed, then y had sent its updated table to its neighbors that there's a change in the cost. Okay, so it's a good news when the cost is reduced, then it's a good news. So it has updated its neighbors with that information. Now Z also, once it receives that information, it tries to update its neighbors. Its neighbor is Y. Y already has the least cost path. It does not change anything once it receives Z's information, so it does not change it further. So this is known as that good news travels fast. Okay, in distance vector algorithms, good news travels fast. Good news being the reduction in the cost between a set of nodes. Now, what happens if this cost, the link cost, now increases? Okay, so earlier it was reducing from 4 to 1, now it is increasing from 4 to 60. So this is the change in the link cost. Now, what would happen? That y is directly connected to x. Okay. Now this link has now changed its cost, and the cost is 60. Okay. And z, it has a path at cost of 5, that is z2y, y2x. Okay, z2x from earlier distance vector, it does have a cost of 5. Okay, so now what will y do? That y will try to find out that, okay, fine, there is a change in the cost and it is 60. If you remember the Bellman-Ford equation, it has to find out from the Bellman-Ford, using the Bellman-Ford equation, that is, what are the different paths, and at each path from a given node to another node, what is the minimum cost, and out of that, the minimum will be taken as the updated value. Right, so what happens here? X to Y, 4 is there, but 4 is now changed to 60. With this change, Y wants to update its information, but Y has an information from Z, that Z somehow has a path from Z to X which costs 5. Okay, and Y knows that Y has a cost of 1 from Y to Z. Okay, so I will think that, okay, somehow Z probably has some path from Z to X which costs 5. So if I take the same path, then it will become 6 and not 60. That has been given with the link with the change in the link cost. Okay. Now, similarly, this information again will get to all the other nodes. Now, they will keep changing their information. So, see in the second point here. So, Z learns that the path to X via Y has a new cost of 6. Okay. So, the path to X via Y. Okay. Remember that if you want to calculate the path from Z to X, you have to find out the cost CZY and D of Y to X, right? So Z gets to know that from Y to X there's a there's a path that costs 6. Okay. Now Z to X, the path is 50, the direct cost path. Right, so now Z will try to compute the new cost, and it will be 7 via Y. Okay, because it thinks that from Y to X somehow the cost is now 6. So with this, from Z to Y the cost becomes 1, and then the total cost from Z to X, it changes to 7. Now again this information goes on, and with this wrong information itself, everybody starts updating their distance vector algorithm, their distance vector tables. Okay. Now this wrong information keeps going on in the network, and this is known as that bad news travels slow. Okay, that means if the cost increases, in that case, this updated change, when we want to send it to the other nodes present in the network, it might lead to a problem, and that problem is known as count to infinity problem. That means this procedure goes on and on, that this one of them gets a wrong distance or wrong information about the weight, and then or it calculates a wrong weight, and then this wrong calculation goes on and on between every other node, nearby node, and they also keep getting that wrong information. Okay, and it takes a really long time to actually find out that, okay, it is not these small weights that we are actually talking about, that does not create that does not define the actual root. In the actual root, the weight has already changed to 60 from 4. Okay, so this actually takes a long time to understand for the network, and by then, of course, everybody else is going to get a wrong information. Okay, so that is why these distributed algorithms are actually tricky, because if there is even a small change, sending that information to every other node present in the network, that becomes very difficult. Okay, so if we have to compare the link state and distance vector algorithms, then what do we know about this? That for link state algorithms, we do have n routers, and O of n square messages are required to be sent. Whereas in distance vector algorithms, there is an exchange of these distance vector estimates between different neighbors, and their convergence time varies. So what's the speed of convergence in case of LS and DV, that is link state and distance vector? For link state algorithm, you have O of n square algorithm. And of course, as we know, when we were using Dijkstra, that you can actually make it to O of n log n. Anyways, but the message complexity, of course, is of O of n square. And it may also have oscillations, that is, routes may change between different nodes at different time intervals. Okay, depending upon what is the amount of traffic that is coming or that is arriving at the particular nodes. For distance vector algorithms, the convergence time varies and it may have routing loops. And of course, the biggest one is that it can have the count to infinity problem, okay, that we have just discussed about. With respect to robustness, that means what happens if the router malfunctions or it is compromised. In those respects, for link state algorithm, the router can actually advertise incorrect link cost, and each router can compute only its own table. So there's a restriction here when it comes to LS algorithms. And for DV, that is distance vector, the router can actually advertise incorrect path cost, okay, which will lead to, which is also known as black holing. Okay, so that is one, and then each router's table, which is used by others, is nothing but it propagates error throughout the network. All right. So please go through the count to infinity problem. It is a very important problem. You will get the same example that I have given. It's already there in Kurosan Ross book. Okay, so please go through it. You can also find out some other examples, or you can create your own examples, different examples than what has been given in the book, and you will find out that, or you can actually get a good grip of what counterinfinity problem is. Okay. Now we are going to do intra-ISP routing, and correspondingly we will look at OSPF routing algorithm. Okay. Now, before we do that, let's see that how to make routing scalable. Okay. So far, what we have considered that, we have not even thought of how the routers are. We have basically assumed that all the routers are identical. They have identical capacities, and the network is flat. Okay. There's no hierarchy in that. Now, this is not true in practice. There are many changes in the router also, and the network is also not flat in nature. So how do we scale the routing? We have billions of destinations, and we cannot store all the destinations in the routing tables. Okay? And if we want to exchange the contents of routing tables, then of course the links will be overly congested, right? So one of them is administrative autonomy. That is, for internet, it is nothing but a network of networks where each network admin may want to control routing in its own network. Okay. So what do we know in over the internet? We have, it is nothing but a connected network of other networks, and in each of these small networks or small network modules, the network admin can or may control the routing within its own network. Okay, so this is known as administrative autonomy. Now, with this comes this concept, okay, that what approach the internet uses to have scalable routing. Okay, so what can be done? We can aggregate routers or clusters from routers and define them as a given region. Right, so this way of aggregating routers and then setting up or defining them into a region is known as autonomous systems, or AS. Okay, so such a scenario or such a system of aggregated routers which are defined or divided into regions is known as an autonomous system or a domain. Okay, So if you want to move from one domain to another or one set of routers to another set of routers, then that is inter-domain routing or inter-AS routing. And if you want to move within the AS itself, then it is intra-AS routing. Okay, so as the definition is given here that intra-AS or your aka intra-domain routing is nothing but routing or among or within the routers of the same AS. Okay, same AS in the sense the same network. Okay. So what are the properties that we need to take care of or features that we need to take care of when we are looking for intra-AS routing? First is that all routers in the AS must run same intra-domain protocol. The routers in different AS can run different intra-domain routing protocols. We are not concerned about it because we are looking for having a communication between devices within the same AS. And of course, the concept of gateway router, which is nothing but that at the edge of its own, that is an an aggregate system or sorry an autonomous system or AS. So at the edge of its own AS, the gateway router has links to routers in other ASs. So nothing but the gateway router acts as a gateway between a given AS and the neighboring ASs. Okay, so this is a very important part when it comes to intra-AS routing or even the entire system of scalable routing using autonomous systems. Okay, so the gateway routers are one of the main components which actually act or which actually are present at the edge of a given AS, and they act as gateways between the outside ASs, all the other ASs or devices which are outside the given AS, and the other devices connected to this AS. Inter-AS routing or inter-domain routing is again another way of communication where the gateways they perform communication between different ASs or between different domains. Okay, so that is why it is known as an inter-domain routing. Um, okay, no, this is not called as intra-domain routing as such. Anyways, okay. So this is how an AS looks like. Okay, so please take a look at the figure here. So you have AS1, AS2, AS3, etc. And each one of these ASs is nothing but an aggregation of different routers here. Okay, 3A, 3B, 3C, 1C, 1A, 1B, 1C, 1D, 2A, 2B, 2C. Okay, now those routers which are acting as a gateway between the routers within the AS and with other routers belonging to other ASs. Those are known as the gateway routers. Okay. If you want to communicate within an AS, then it is intra-AS routing. If you want to communicate between different ASs, then it is known as inter-AS routing. Okay. All right. So, yeah, so this is what I just told. Okay. Okay, so these are so there can be forwarding table configured by intra and inter-AS routing algorithms, and accordingly decisions can be taken when you are trying to move either out of a given or whether the communication is happening inter-AS or intra-AS. Okay. All right, so I will repeat this slide again in the next class because we are already out of time, so I don't want to stretch it further, but I'll just finish this slide. So we do have a forwarding table which is configured by both or which is influenced by both intra-AS routing algorithm and inter-AS routing algorithm, as you can see here. Okay, so you have entries correspondingly. All right. Okay, so this is where I will stop the class for today. If you have any questions, please go ahead and ask. If not, then I'll stop the class for today.